close your eyes. Take a slow breath. Tonight we're going somewhere extraordinary, not by leaving Earth, but by understanding where Earth truly is. We live on a planet that orbits a star, and that star is one small point of light among hundreds of billions. Together they form a structure so vast, so ancient, that human minds struggle to hold its full measure. This is the Milky Way, our galactic home. For most of human history, we didn't know we lived in a galaxy at all. The pale band of light stretching across the night sky, what ancient Greeks called Galaxius Kyklos, the Milky Circle, was a mystery. Some thought it was a river of milk spilled by the goddess Hera. Others believed it was the road souls travelled to the afterlife. It wasn't until the early 20th century that we understood the truth. We are inside it, looking out from within. Fact 1. The Milky Way is a barred spiral galaxy. Our galaxy belongs to a specific family of cosmic structures. Astronomers classify it as a barred spiral galaxy, a designation that tells us about its shape and internal architecture. Imagine looking down from above the galactic plane. From a vantage point billions of miles above the disk, you would see a flat, rotating wheel of stars with graceful arms spiraling outward from the center. But unlike a simple spiral, our galaxy has a bar, a dense, elongated structure of stars cutting through the core like the handle of a cosmic whisk. This bar wasn't always known to us. For decades, astronomers debated whether the Milky Way had one. The problem is perspective. We're embedded inside the disk, roughly 26,000 light-years from the center, trying to map the whole structure from within. It's like trying to draw a map of a vast city while standing in the middle of one neighborhood, with buildings blocking your view in every direction. Only in the 1990s, using infrared observations that could peer through the dust, did we confirm the bar's existence. It stretches about 27,000 light-years from end to end, and it rotates, though not at the same speed as the spiral arms. Why does the bar exist? It's a consequence of gravitational instabilities. In the dense inner regions of the galaxy, stars don't orbit in perfect circles. Their orbits become elongated, and over millions of years these elongated orbits align, creating a bar-shaped concentration of stars. This bar plays a crucial role in the galaxy's evolution. It funnels gas from the outer regions toward the center, feeding star formation and, as we'll see later, feeding the supermassive black hole that lurks at the galaxy's heart. Fact 2. The Milky Way contains between 100 and 400 billion stars. How many stars are there in our galaxy? It's one of the most fundamental questions in astronomy, and the answer is surprisingly uncertain. Current estimates place the number somewhere between 100 billion and 400 billion stars. That's a huge range, a factor of 4 difference between the low and high estimates. Why such uncertainty? The problem is that most stars in the Milky Way are dim. Our Sun is actually brighter than about 85% of all stars in the galaxy. The majority are red dwarfs, small, cool stars that burn their fuel so slowly they can live for trillions of years, far longer than the current age of the universe. These red dwarfs are incredibly faint. Even the nearest red dwarf, Proxima Centauri, is invisible to the naked eye despite being only 4.2 light-years away. Counting them across the entire galaxy is extraordinarily difficult. Astronomers use several methods to estimate the total stellar population. One approach is to count stars in a small representative region of the galaxy, and then extrapolate to the whole structure. Another method involves measuring the total mass of the galaxy, and subtracting the contributions from dark matter, gas and dust to get the stellar mass, then dividing by the average mass of a star. Each method has uncertainties, and they don't always agree. But let's pause and consider what 100 billion stars actually means. If you counted 1 star per second without stopping to eat or sleep, it would take you more than 3,000 years to count them all. And that's the low estimate. The Milky Way is not just big, it's incomprehensibly populous. A city of suns so vast that our entire recorded history is a blink in the time it would take to catalogue its inhabitants. Fact 3. The galaxy is approximately 6 billion years old. The Milky Way is ancient. Current estimates place its age at around 13.6 billion years, which means it formed only about 200 million years after the Big Bang itself. The universe is 13.8 billion years old, so our galaxy has existed for nearly the entire history of the cosmos. How do we know this? Astronomers use several techniques to date the galaxy. One of the most reliable involves studying the oldest stars we can find. Stars are like cosmic clocks. Their internal processes tick at predictable rates determined by the laws of nuclear physics. By analyzing the chemical composition and brightness of ancient stars, particularly those in globular clusters, dense spherical collections of old stars that orbit the galaxy, we can calculate how long they've been burning. The oldest stars in the Milky Way are found in the halo, a roughly spherical region surrounding the galactic disk. These stars are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. This makes sense. They formed when the universe was young, before generations of stars had lived and died, enriching space with the heavier elements forged in their cores and scattered in supernova explosions. One of the oldest known stars in our galaxy is called HD 140283, sometimes nicknamed the Methuselah star. For a while it caused astronomers some concern because initial age estimates suggested it might be older than the universe itself, an obvious impossibility. Refined measurements have since placed its age at around 14.5 billion years, with an uncertainty range that comfortably overlaps with the age of the universe. This star is a relic, a survivor from the galaxy's infancy. The Milky Way didn't form all at once. It grew over time, accreting smaller galaxies and clouds of gas. The oldest parts, the central bulge and the halo, formed first in a chaotic, violent process. The disk, where most star formation happens today, assembled more gradually. We live in a galaxy that is still, in some sense, under construction. Fact 4. Our solar system orbits the galactic center at about 515,000 miles per hour right now. As you sit still, you are moving at an extraordinary speed. Earth orbits the Sun at about 67,000 miles per hour. But the Sun itself is not stationary. It orbits the center of the Milky Way, carrying Earth and all the other planets with it at a speed of roughly 515,000 miles per hour, or about 230 kilometers per second. At this velocity, it takes the Sun approximately 225 to 250 million years to complete one orbit around the galaxy. Astronomers call this period a galactic year or cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits. 20 times our star has traced its long, looping path through the spiral arms, through regions dense with gas and dust, and through the quieter spaces between. Think about what this means for Earth's history. The last time the Sun was in this position in its orbit, the age of dinosaurs had not yet begun. The continents were arranged differently. Life was simpler, smaller. 1 galactic year ago, the most complex life on Earth was still confined to the oceans. The Sun's motion through the galaxy is a slow, majestic waltz, and we are passengers on a journey that spans deep time. But the Sun's orbit is not a perfect circle. It bobs up and down relative to the galactic plane, oscillating above and below the disk with a period of about 70 million years. Some scientists have speculated that these oscillations might influence Earth's climate or even the rate of mass extinctions, as the solar system passes through denser regions of the disk where gravitational interactions and radiation might be more intense. The evidence for this is debated, but it's a reminder that our galactic environment is not static. We are part of a dynamic, ever-changing system. Fact 5. The Milky Way's disk is about 1,000 light-years thick. If you could view the Milky Way edge-on, you'd see a thin disk of stars, gas, and dust. The disk is the most prominent feature of the galaxy, and it's where most of the action happens, where stars are born, where planets form, where the spiral arms trace their glowing patterns. But despite its vast diameter, the disk is remarkably thin. The main stellar disk is about 1,000 light-years thick. To put that in perspective, the disk's diameter is roughly 100,000 light-years, which means the ratio of diameter to thickness is about 100 to 1. If you scaled the Milky Way down to the size of a dinner plate, the disk would be thinner than a sheet of paper. This thinness is a consequence of rotation and gravity. When the galaxy formed, gas and dust collapsed under gravity, but because the cloud was rotating, it couldn't collapse into a sphere. Instead, it flattened into a disk, with the rotation providing outward centrifugal support against gravity in the plane of the disk, while gravity pulled material together perpendicular to that plane. The result is a flat, spinning structure. But the disk is not uniform. There's actually a thin disk and a thick disk. The thin disk where the Sun resides is about 1,000 light-years thick and contains younger stars, gas, and active star formation. The thick disk is older, about 3,000 light-years thick, and contains stars that formed earlier in the galaxy's history. These two components overlap, and the Sun sits right in the middle of the thin disk, about 45 light-years above the midplane, a trivial offset on galactic scales. The thinness of the disk has profound implications. It means that stars in the disk are relatively close together in the vertical direction, even though they're spread out over vast distances horizontally. It also means that the disk is fragile. Gravitational interactions with passing galaxies or dark matter clumps can create ripples and warps in the disk, like waves on a pond. Astronomers have detected such warps in the outer regions of the Milky Way, evidence of past disturbances. Fact 6. The galactic halo extends far beyond the visible disk. Beyond the bright disk of stars lies the halo, a vast, roughly spherical region that envelops the entire galaxy. The halo is much larger than the disk. It extends out to at least 200,000 light-years from the galactic center, and possibly much farther. But it's also much more diffuse. The halo contains only about 1% of the galaxy's stars, scattered thinly through an enormous volume of space. The stars in the halo are different from those in the disk. They're old, metal-poor, and they move in highly elliptical orbits that take them plunging through the disk and then back out into the halo's outer reaches. Many of these stars are found in globular clusters, dense, spherical collections of hundreds of thousands of stars, all born around the same time. The Milky Way has about 150 known globular clusters, and they orbit the galaxy like distant moons. But the halo is not just stars. It's also where most of the galaxy's dark matter resides. Dark matter is a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to telescopes. We know it exists because of its gravitational effects. It holds galaxies together and shapes the large-scale structure of the universe. In the Milky Way, dark matter outweighs ordinary matter by a factor of about 10 to 1. The halo is dominated by this invisible mass, forming a vast dark cocoon around the visible galaxy. The halo also contains hot gas, heated to millions of degrees by supernova explosions and other energetic processes. This gas is so hot that it emits X-rays, and astronomers have mapped it using space-based X-ray telescopes. The halo is not empty space. It's a dynamic, complex environment, filled with the remnants of the galaxy's violent past. Fact 7. The Milky Way formed from the collapse of a primordial gas cloud. The story begins in the early universe, less than 1 billion years after the Big Bang. At that time, the universe was filled with vast clouds of hydrogen and helium gas, the primordial elements forged in the first minutes after the Big Bang. These clouds were not perfectly uniform. Tiny density fluctuations, seeded by quantum fluctuations in the very early universe, created regions where the gas was slightly denser than average. Gravity amplified these fluctuations. Denser regions attracted more gas, becoming denser still, in a runaway process. Over millions of years, these regions collapsed under their own gravity, forming the first structures in the universe. Some of these collapsing clouds became the seeds of galaxies. The Milky Way's formation was not a simple, orderly process. It was chaotic and violent. The initial collapse created a roughly spherical cloud of gas which fragmented into smaller clumps. These clumps became the first stars, massive, short-lived giants that burned fiercely and died in supernova explosions, enriching the surrounding gas with heavier elements. These first stars formed what would become the galactic halo. As the cloud continued to collapse, it began to rotate. Conservation of angular momentum, a fundamental law of physics, meant that as the cloud shrank, it spun faster, like a figure skater pulling in their arms. The rotation prevented the cloud from collapsing into a single point. Instead, it flattened into a disk, with the rotation providing outward support against gravity. The disk became the site of ongoing star formation. Gas in the disk cooled and fragmented, forming new generations of stars. These stars were richer in heavy elements than the first generation because they formed from gas enriched by earlier supernovae. Over billions of years, the disk grew and evolved, developing the spiral arms and bar structure we see today. But the Milky Way didn't form in isolation. It grew by consuming smaller galaxies. Throughout its history, the Milky Way has cannibalized dozens, perhaps hundreds of smaller galaxies that wandered too close. These mergers added stars to the halo and disk, and they stirred up the galaxy's structure, creating streams of stars that trace the paths of the devoured galaxies. We are living in a galaxy built from the remnants of many smaller systems. Fact 8. The oldest stars in the Milky Way are found in globular clusters. Globular clusters are among the most beautiful objects in the night sky. Through a telescope, they appear as dense, spherical swarms of stars, glowing like cosmic beehives. The Milky Way has about 150 known globular clusters, and they are relics from the galaxy's earliest days. Each globular cluster contains hundreds of thousands of stars, all packed into a region only a few dozen light-years across. This makes them incredibly dense by astronomical standards. In the core of a globular cluster, stars are separated by distances of only a light week or so, far closer than stars in the Sun's neighbourhood, where the nearest star is over 4 light-years away. If Earth were located in the core of a globular cluster, the night sky would be ablaze with thousands of bright stars, casting shadows and rendering the darkness of night a thing of the past. The stars in globular clusters are old, typically 10 to 13 billion years old, nearly as old as the universe itself. They formed in the early stages of the Milky Way's assembly, when the galaxy was still a chaotic, collapsing cloud of gas. Because they're so old, these stars are metal poor. In astronomical terms, metals means any element heavier than hydrogen and helium. The first stars in the universe had no metals at all, because metals are forged inside stars and scattered into space when stars die. The stars in globular clusters have some metals but far less than the Sun, indicating they formed early, before many generations of stars had lived and died. Studying globular clusters allows astronomers to probe the early history of the galaxy. By measuring the ages and chemical compositions of their stars, we can piece together a timeline of the Milky Way's formation. We can also test theories of stellar evolution. Because all the stars in a cluster formed at the same time from the same cloud of gas, providing a controlled experiment in how stars of different masses age. Globular clusters orbit the galaxy in the halo, on highly elliptical paths that take them far from the galactic plane. Some pass through the disk, creating brief, spectacular encounters. Over billions of years, gravitational interactions with the disk and with other clusters can strip stars away from a globular cluster, slowly dissolving it. Some clusters have already been destroyed, leaving behind streams of stars that trace their former orbits. Fact 9. The Sun is located in the Orion Arm, a minor spiral arm. The Milky Way spiral arms are one of its most striking features. These arms are regions of higher density, where stars, gas, and dust are concentrated. They glow brightly because they're sites of active star formation filled with young, hot blue stars and glowing nebulae. But the spiral arms are not solid structures. They're more like traffic jams, regions where stars and gas slow down and pile up as they orbit the galaxy. The Milky Way has 4 major spiral arms: the Perseus Arm, the Scutum Centaurus Arm, the Norma Arm, and the Sagittarius Arm. These arms wind outward from the central bar, tracing graceful logarithmic spirals. But there are also smaller minor arms, and the Sun is located in one of these, the Orion Arm, also called the Orion Spur. The Orion Arm is a minor structure, a spur that branches off between the larger Perseus and Sagittarius arms. It's about 10,000 light-years long and 3,500 light-years wide. The Sun sits roughly in the middle of this arm, about 26,000 light-years from the galactic center. Our location is not particularly special. We're in a quiet suburban region of the galaxy, far from the crowded, chaotic center and far from the sparse, lonely outer edges. Being in a spiral arm has consequences. Spiral arms are regions of higher stellar density, which means more frequent gravitational interactions and a higher rate of supernovae. Some scientists have speculated that the Sun's passage through spiral arms might influence Earth's climate or the rate of mass extinctions, but the evidence is inconclusive. What is clear is that our location in the Orion Arm gives us a particular view of the galaxy. When we look toward the constellation Sagittarius, we're looking toward the galactic center through the densest parts of the disk. When we look toward Perseus, we're looking outward toward the outer arms. The spiral arms themselves are not permanent features. They're density waves, patterns that rotate through the disk at a different speed than the stars and gas. Stars drift in and out of the arms as they orbit the galaxy, spending some time in the dense arm regions and some time in the quieter inter-arm regions. The arms persist because they're maintained by gravitational forces, but the individual stars and gas clouds that make them up are constantly changing. Fact 10. The Milky Way is part of the local group of galaxies. The Milky Way is not alone. It's part of a small cluster of galaxies called the local group, which contains about 80 known galaxies spread across a region roughly 10 million light-years in diameter. Most of these galaxies are small, faint dwarf galaxies, but the local group also contains 3 large spiral galaxies: the Milky Way, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. The Milky Way and Andromeda are the 2 dominant members of the local group, each with its own retinue of satellite galaxies. The Milky Way has at least 59 known satellite galaxies, including the large and small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere. These satellites orbit the Milky Way bound by its gravity, and over time some of them will be torn apart and absorbed, adding their stars to the Milky Way's halo. The local group is bound together by gravity. All the galaxies within it are moving relative to one another, but they're not flying apart. They're gravitationally bound, orbiting a common center of mass. The Milky Way and Andromeda are actually moving toward each other, and in about 4.5 billion years, they will collide and merge, forming a single, larger galaxy that astronomers have nicknamed Milkomeda. Being part of the local group shapes the Milky Way's evolution. Interactions with satellite galaxies stir up the disk, creating warps and ripples. The ongoing accretion of smaller galaxies adds mass and angular momentum. The local group is also part of a larger structure called the Virgo supercluster, a vast collection of galaxy groups and clusters spanning hundreds of millions of light years. On the largest scales, the universe is a cosmic web of galaxies, and the Milky Way is one small thread in that immense tapestry. Fact 11. The galactic coordinate system uses the galactic center as its reference point to map the Milky Way. Astronomers use a special coordinate system called the galactic coordinate system. Unlike the familiar celestial coordinate system, which is based on the structure of the galaxy itself, in this system, the galactic center defines the 0 point of longitude. Latitude is measured relative to the galactic plane, the flat disk of the galaxy. The North Galactic Pole points perpendicular to the disk in the direction of the constellation Coma Berenices, while the South Galactic Pole points toward the constellation Sculptor. This coordinate system is essential for studying the galaxy's structure. When astronomers plot the positions of stars, gas clouds, or other objects in galactic coordinates, patterns emerge that would be hidden in other coordinate systems. The spiral arms, the bar, the warp in the outer disk, all of these features become clear when viewed in the galaxy's own reference frame. But using galactic coordinates also highlights a fundamental challenge. We're trying to map a structure from inside it. Imagine trying to draw a map of a forest while standing in the middle of it, with trees blocking your view in every direction. That's the challenge astronomers face. We can't step outside the galaxy to see it from above. We have to infer its structure from observations made from our single vantage point, using clever techniques and careful measurements. One of the most powerful tools for mapping the galaxy is astrometry, the precise measurement of stellar positions and motions. By tracking how stars move over time, astronomers can reconstruct the galaxy's rotation curve, the distribution of mass, and the shapes of the spiral arms. Space missions like Gaia, which has measured the positions and motions of over 1 billion stars, have revolutionized our understanding of the Milky Way's structure. Fact 12. The Milky Way's total mass is about 1.5 trillion times the mass of the Sun. How much does the Milky Way weigh? It's a deceptively simple question with a complex answer. The total mass of the galaxy is estimated to be about 1.5 trillion solar masses. That is, 1.5 trillion times the mass of the Sun. But most of this mass is not in stars, gas, or dust. It's in dark matter, ordinary matter. The stuff that makes up stars, planets, and us accounts for only about 10% of the galaxy's total mass. The rest is dark matter, an invisible substance that we detect only through its gravitational effects. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly, but we know it's there because of how it influences the motion of stars and gas. One of the key pieces of evidence for dark matter comes from the galaxy's rotation curve. If the Milky Way contained only the matter we can see, stars in the outer regions should orbit more slowly than stars closer to the center, just as outer planets in the solar system orbit more slowly than inner planets. But observations show that stars in the outer galaxy orbit at roughly the same speed as stars closer in. This can only be explained if there's a large amount of unseen mass, dark matter, distributed throughout the galaxy, extending far beyond the visible disk. Measuring the galaxy's total mass is challenging. Astronomers use several methods, including studying the orbits of satellite galaxies, measuring the velocities of stars and gas, and analyzing the gravitational lensing of distant objects. Each method has uncertainties, and they don't always agree perfectly, which is why estimates of the Milky Way's mass have a range. But even with the uncertainties, the scale is staggering. 1.5 trillion solar masses. If you could somehow gather all that mass into one place, it would form a black hole, With an event horizon larger than the orbit of Neptune, the Milky Way is not just a collection of stars, it's a gravitational behemoth, a massive structure held together by the invisible hand of dark matter, slowly rotating through the cosmos. The spiral arms of the Milky Way are among the most beautiful structures in the cosmos. They wind outward from the galactic center like the arms of a cosmic hurricane, glowing with the light of billions of stars. But these arms are not what they seem. They are not solid structures, not permanent features carved into the galaxy. They are waves, density waves, patterns that move through the disk like ripples on a pond, concentrating stars and gas into luminous streams that trace the galaxy's rotation. Tonight we explore these arms. We'll discover why they exist, how they shape the galaxy's evolution, and what it means to live inside one. We'll meet the young stars that make the arms glow, the vast clouds of gas where new stars are born, and the forces that drive this grand, slow dance through space. Fact 13. Spiral arms are density waves, not fixed structures. When you look at an image of a spiral galaxy, it's natural to assume that the spiral arms are like the arms of a pinwheel, solid structures that rotate as a unit. But this is not how spiral arms work. They are density waves, regions where stars and gas are temporarily concentrated as they move through the disk. Imagine cars on a highway. Sometimes traffic slows down, creating a jam. Cars enter the jam from behind, slow down, and then speed up again as they exit the front of the jam. The jam itself, the region of high density, moves along the highway at its own speed, which is different from the speed of the individual cars. The cars flow through the jam, but the jam persists. Spiral arms work the same way. Stars and gas orbit the galaxy at their own speeds, determined by their distance from the center. But as they orbit, they encounter regions of higher gravitational potential, the spiral arms. In these regions, they slow down slightly, bunching up and increasing the local density. Then they exit the arm and speed up again. The arm itself, the density wave, rotates at a different speed than the stars, typically slower. This is called the winding problem, and it's one of the key insights that led to the density wave theory. The theory was developed in the 1960s by astronomers C.C. Lin and Frank Hsu. Before their work, it was unclear how spiral arms could persist. If the arms were made of the same stars rotating together, they would wind up tighter and tighter over time, eventually becoming unrecognizable. But if the arms are density waves, they can maintain their shape indefinitely, even as individual stars drift in and out. The density wave is maintained by gravity. The extra mass in the arm creates a gravitational potential that attracts more stars and gas, reinforcing the wave. It's a self-sustaining pattern, a standing wave in the gravitational field of the galaxy. The arms are not made of specific stars, they're made of whichever stars happen to be passing through at any given time. This has profound implications. It means the spiral arms are dynamic, constantly refreshed by new material. It also means that the Sun, as it orbits the galaxy, drifts in and out of spiral arms. Sometimes we're in an arm surrounded by young stars and glowing nebulae. Sometimes we're in the quieter inter-arm regions. Right now we're in the Orion Spur, a minor arm, but over the course of the Sun's orbit we'll pass through several major arms. Fact 14. The Milky Way has 4 major spiral arms. The Milky Way spiral structure has been debated for decades. Early maps suggested 2 arms, then 4, then back to 2. The problem is that we're inside the galaxy, trying to map it from within, and dust in the disk blocks our view of distant regions. Only with the advent of infrared and radio telescopes, which can see through the dust, have we been able to piece together a clearer picture. Current evidence suggests the Milky Way has 4 major spiral arms. the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. These arms wind outward from the central bar, tracing logarithmic spirals, curves where the angle between the arm and a radial line from the center remains constant. The Perseus arm is one of the most prominent. It lies outside the Sun's orbit, about 600 and 500 light-years away in the direction of the constellation Perseus. It's rich in young stars and star-forming regions, including the famous California Nebula and the Double Cluster. The Scutum Centaurus arm is the longest and most massive of the arms. It stretches across a huge arc of the galaxy, from the constellation Scutum through Centaurus. This arm contains some of the galaxy's most active star-forming regions, including the Omega Nebula and the Eagle Nebula, home of the iconic Pillars of Creation. The Norma arm is less well studied because it lies on the far side of the galaxy, obscured by the dense star fields of the galactic center. But radio observations have revealed it to be a significant structure, rich in molecular gas. The Sagittarius arm lies between the Sun and the galactic center. When we look towards Sagittarius on a summer night, we're looking along this arm, through the densest parts of the Milky Way. The view is spectacular, a river of stars and dark dust lanes stretching across the sky. In addition to these major arms, there are minor arms and spurs, including the Orion Spur where the Sun resides. These smaller structures may be branches off the major arms, or they may be transient features created by local gravitational instabilities. The exact structure of the Milky Way's spiral pattern is still being refined as new data comes in from surveys like Gaia and Apogee. Fact 15. Spiral arms are sites of active star formation. The spiral arms glow brightly because they're where stars are born. The density wave compresses the gas in the disk, and when gas is compressed it cools and fragments, collapsing under its own gravity to form stars. This is why the arms are filled with young, hot, blue stars, massive stars that burn fiercely and die quickly, living only a few million years. These young stars are so bright that they dominate the light from the spiral arms, making the arms stand out against the rest of the disk. But the arms also contain older stars, red and yellow stars like the Sun, that happen to be passing through. The difference is that the old stars are spread more evenly throughout the disk, while the young stars are concentrated in the arms, marking the sites of recent star formation. The process of star formation in spiral arms is complex. It begins with giant molecular clouds, vast cold clouds of hydrogen gas, laced with dust and trace amounts of other molecules like carbon monoxide. These clouds are the raw material for stars. They're enormous, containing tens of thousands to millions of solar masses of gas, and they can be hundreds of light years across. When a molecular cloud enters a spiral arm, the density wave compresses it. This compression can trigger gravitational collapse. Parts of the cloud become dense enough that gravity overcomes the internal pressure of the gas, and the cloud fragments into smaller clumps. Each clump continues to collapse, heating up as gravitational potential energy is converted to thermal energy. Eventually, the core of the clump becomes hot and dense enough for nuclear fusion to ignite, and a star is born. But not all the gas in a molecular cloud becomes stars. Much of it is blown away by the intense radiation and stellar winds from the newly formed stars, especially the most massive ones. These massive stars are like cosmic blowtorches, carving out cavities in the surrounding gas and triggering further star formation in the compressed edges of the cloud. This process can create a cascade of star formation, with each generation of stars triggering the next. The spiral arms are also where we find the most spectacular nebulae, glowing clouds of gas ionized by the ultraviolet light of young hot stars. These nebulae are the visible signposts of star formation, glowing in the characteristic red light of hydrogen alpha emission. They're beautiful, but they're also fleeting. Within a few million years, the stars will disperse, the gas will be blown away and the nebula will fade, leaving behind only a cluster of stars drifting through the disk. Hash, hash, hash. Fact 16. The Perseus Arm contains the famous double cluster. The Perseus Arm is home to one of the most beautiful sights in the night sky, the double cluster, also known as NGC 869 and NGC 884. These are two open star clusters, each containing hundreds of young, hot stars, located about 7,500 light-years from Earth. They're close together in space, only a few hundred light-years apart, and they're visible to the naked eye as a hazy patch in the constellation Perseus. Through binoculars or a small telescope, the double cluster is stunning. The two clusters are packed with bright blue and white stars, many of them supergiants, stars dozens of times more massive than the Sun. These stars are young, only about 12 to 13 million years old, which is a blink of an eye in cosmic terms. They formed from the same giant molecular cloud, and they're still close together, though over time they'll drift apart as they orbit the galaxy. The double cluster is a reminder of the youth and vitality of the spiral arms. These clusters are stellar nurseries, places where stars are born in large groups. Most stars, including the Sun, are thought to have formed in such clusters, but over time the clusters disperse. Gravitational interactions between the stars and with passing gas clouds gradually pull the cluster apart, scattering its stars across the galaxy. The Sun was likely born in a cluster similar to the double cluster, but that cluster has long since dissolved, and the Sun's siblings are now scattered across the Milky Way, indistinguishable from other stars. Open clusters like the double cluster are different from the globular clusters we discussed in Chapter 1. Globular clusters are old, dense, and spherical, containing hundreds of thousands of stars. Open clusters are young, loose, and irregular, containing dozens to thousands of stars. They're found in the disk, especially in the spiral arms, while globular clusters orbit in the halo. Open clusters are laboratories for studying star formation and stellar evolution, because all the stars in a cluster are the same age and formed from the same material, allowing astronomers to isolate the effects of mass on a star's life cycle. Fact 17. The Scutum Centaurus Arm hosts the Eagle Nebula. The Scutum Centaurus Arm is one of the galaxy's most active star-forming regions, and it's home to the Eagle Nebula, one of the most iconic objects in astronomy. The Eagle Nebula, also known as M16, is a vast cloud of gas and dust about 7,000 light-years from Earth. It's a stellar nursery, a place where new stars are being born right now. The most famous feature of the Eagle Nebula is the Pillars of Creation, 3 towering columns of gas and dust photographed by the Hubble Space Telescope in 1995. The image became one of the most recognizable in all of astronomy, a testament to the beauty and power of the universe. The pillars are several light-years tall, and they're being sculpted by the intense ultraviolet radiation from nearby young stars. The radiation erodes the gas, but denser clumps resist the erosion, creating the pillar shapes. Inside the pillars, new stars are forming. The dense clumps of gas are collapsing under their own gravity, and in some cases, they've already formed protostars, infant stars still surrounded by cocoons of gas and dust. These protostars are invisible in optical light, but they glow brightly in infrared, which can penetrate the dust. Infrared observations have revealed dozens of protostars embedded in the pillars. But the pillars of creation are doomed. A supernova explosion from a nearby massive star likely destroyed them about 6,000 years ago. The shockwave from the supernova would have swept through the nebula, compressing and heating the gas and eventually dispersing the pillars. But because the nebula is 7,000 light-years away and light takes time to travel, we won't see the destruction for another 1,000 years. For now, the pillars still stand in our sky, a monument to the ongoing cycle of stellar birth and death. The Eagle Nebula is also home to an open star cluster, NGC 6611, which contains the young, hot stars responsible for ionizing the nebula and sculpting the pillars. These stars are only a few million years old, and they're among the most massive stars in the galaxy, with masses up to 80 times that of the Sun. They burn their fuel at a prodigious rate, and they'll live only a few million years before exploding as supernovae, enriching the surrounding gas with heavy elements and triggering new rounds of star formation. Fact 18. Molecular clouds in the arms contain millions of solar masses of gas. The raw material for star formation is molecular hydrogen gas, and it's concentrated in giant molecular clouds. These clouds are the largest structures in the galaxy, containing anywhere from tens of thousands to millions of solar masses of gas. They're cold, only about 10 to 20 degrees above absolute zero, and they're dense by interstellar standards, though still far more tenuous than the best vacuum we can create on Earth. Molecular clouds are found throughout the disk, but they're especially common in the spiral arms, where the density wave compresses the gas and triggers cloud formation. The largest molecular clouds are called giant molecular cloud complexes, and they can be hundreds of light years across. These complexes are the sites of the most vigorous star formation in the galaxy. One of the nearest giant molecular cloud complexes is the Orion Molecular Cloud Complex, located about 1,500 light-years from Earth in the constellation Orion. This complex contains several distinct clouds, including the Orion A and Orion B clouds, and it's actively forming stars. The Orion Nebula, visible to the naked eye as the middle star in Orion's sword, is a small, bright region on the surface of the Orion A cloud, where hot young stars are ionizing the surrounding gas. Molecular clouds are difficult to observe directly because they're so cold that they don't emit much light, but they do emit radio waves, particularly from molecules like carbon monoxide, CO, which is easier to detect than molecular hydrogen. By mapping the radio emission from CO, astronomers can trace the distribution of molecular clouds throughout the galaxy and measure their masses. The life cycle of a molecular cloud is tied to star formation. Clouds form from the accumulation of atomic hydrogen gas which cools and becomes molecular. Over time, parts of the cloud collapse to form stars. The most massive stars produce intense radiation and stellar winds that heat and disperse the surrounding gas, eventually destroying the cloud. The entire process from cloud formation to dispersal takes only a few tens of millions of years, a brief moment in the galaxy's history. Fact 19. The Sagittarius arm lies between the Sun and the galactic center when you look toward the heart of the Milky Way. The galactic center lies in that direction, about 26,000 light-years away, hidden behind thick clouds of dust. But between us and the center lies the Sagittarius arm, one of the galaxy's major spiral arms. The Sagittarius arm is rich in star-forming regions and young star clusters. It's one of the most prominent features of the Milky Way when viewed from Earth, because we're looking along its length through the densest concentrations of stars and gas. The view is spectacular, a glowing river of light stretching across the sky, punctuated by dark dust lanes and bright nebulae. Some of the most famous objects in the night sky are located in the Sagittarius arm. The Lagoon Nebula, the Trifid Nebula, and the Omega Nebula are all part of this arm, glowing with the light of newly formed stars. These nebulae are among the brightest in the sky, and they're favourite targets for amateur astronomers. The Sagittarius arm also contains numerous open star clusters including M21, M23, and M25. These clusters are young, containing hot blue stars that light up the surrounding gas. They're part of the ongoing cycle of star formation in the arm, where molecular clouds collapse, form stars, and then disperse, leaving behind clusters that gradually dissolve over hundreds of millions of years. Looking towards Sagittarius, we're also looking through the most crowded part of the sky. The density of stars in that direction is so high that it's difficult to distinguish individual stars in photographs. The Milky Way appears as a continuous glow, a band of light made up of billions of unresolved stars. This is the view that inspired ancient astronomers and storytellers, who saw in the Milky Way a river, a road, or a bridge between worlds. Fact 20. Dust lanes trace the inner edges of spiral arms, one of the most striking features of spiral galaxies, when viewed edge-on or at an angle, is the dark dust lanes that trace the spiral arms. These lanes are not empty, they're filled with dust, tiny grains of solid material made of carbon, silicon, and other elements. The dust absorbs and scatters light, creating dark silhouettes against the background glow of stars. In the Milky Way, dust lanes mark the inner edges of the spiral arms, where the density wave compresses the gas and dust. The compression creates a shock front, a region where the gas suddenly slows down and piles up. Behind the shock front, the gas is compressed and cooled, creating ideal conditions for molecular cloud formation and star formation. Ahead of the shock front, the gas is more diffuse and less active. The dust itself is a byproduct of stellar evolution. It's formed in the outer atmospheres of cool, evolved stars like red giants, and it's also produced in supernova explosions. The dust grains are tiny, typically less than a micrometer across, smaller than the width of a human hair. But there are so many of them that they have a profound effect on the appearance of the galaxy. Dust doesn't just block light, it also reddens it. Blue light is scattered more efficiently than red light, so when starlight passes through dust, the blue light is scattered away, and the remaining light appears redder. This is the same effect that makes sunsets red on Earth. In the galaxy, dust reddening makes distant stars appear dimmer and redder than they actually are, which complicates efforts to measure distances and map the galaxy's structure. But dust is also essential for star formation. The dust grains provide surfaces where hydrogen atoms can combine to form molecular hydrogen, the main ingredient for stars. Without dust, the conversion from atomic to molecular hydrogen would be much slower, and star formation would be less efficient. Dust also helps cool the gas by radiating away heat, allowing molecular clouds to collapse more easily. Infrared telescopes can see through the dust, revealing the hidden structure of the galaxy. Observations at infrared wavelengths have shown that the dust lanes are teeming with activity. Young stars, protostars, and dense molecular clouds, all invisible in optical light but glowing brightly in the infrared. Fact 21. The Orion Spur is about 10,000 light-years long. The Sun resides in a minor spiral arm called the Orion Spur, also known as the Orion Arm or the Orion Cygnus Arm. It's a small structure compared to the major arms, stretching about 10,000 light-years in length. The spur lies between the larger Perseus and Sagittarius arms, and it's thought to be a branch or offshoot of one of the major arms, though its exact nature is still debated. The Orion Spur is named after the constellation Orion, which lies in the direction of the spur when viewed from Earth. It contains many well-known star-forming regions, including the Orion Nebula, the Rosette Nebula, and the North American Nebula. These regions are relatively nearby, within a few thousand light-years, which makes them ideal targets for detailed study. The Sun is located roughly in the middle of the Orion Spur, about 26,000 light-years from the galactic center. Our position is not particularly special, but it does give us a particular perspective on the galaxy. We're far enough from the center to avoid the crowded, chaotic conditions there, but close enough to be in a region of active star formation. We're in a quiet suburban neighborhood where stars are spaced far apart and the pace of life is slow. The Orion Spur is also where we find many of the nearest stars to the Sun. Alpha Centauri, the nearest star system, is only 4.4 light-years away and it's part of the Spur. Sirius, the brightest star in the night sky, is 8.6 light-years away, also in the Spur. These nearby stars are our immediate neighbours in the galaxy, and they're the stars we're most likely to explore first if we ever develop interstellar travel. The structure of the Orion Spur is still being mapped. Recent observations from the Gaia mission have revealed the three-dimensional positions and motions of millions of stars in the spur, allowing astronomers to trace its shape and understand its dynamics. The spur appears to be a coherent structure, with stars moving together in a coordinated way, suggesting it's a real feature of the galaxy and not just a random clump of stars. Fact 22. Spiral arms can trigger bursts of star formation. The passage of a spiral arm through a region of the disk can trigger intense bursts of star formation. The density wave compresses the gas, creating conditions ripe for gravitational collapse. But the effect is not uniform. It depends on the local conditions, the amount of gas available, and the strength of the density wave. In some regions, the passage of a spiral arm can trigger a starburst, a period of exceptionally rapid star formation, where stars form at rates hundreds or even thousands of times higher than the galactic average. These starbursts are brief, lasting only a few million years, but they can have a profound impact on the galaxy's evolution. They produce large numbers of massive stars which quickly die in supernova explosions, enriching the surrounding gas with heavy elements and injecting energy into the interstellar medium. Starbursts are more common in the central regions of galaxies, where the gas density is higher and the gravitational forces are stronger. But they can also occur in the spiral arms, especially where two arms intersect or where the density wave is particularly strong. The result is a bright, glowing region filled with young stars and ionized gas, visible across vast distances. The triggering of star formation by spiral arms is a key part of the galaxy's self-regulation. Star formation consumes gas, converting it into stars, but the massive stars produced in the spiral arms quickly die and return much of their mass to the interstellar medium, enriched with heavy elements. This recycled gas can then form new stars, continuing the cycle. The spiral arms act as a pacemaker, regulating the rate of star formation and ensuring that the galaxy doesn't exhaust its gas supply too quickly. Computer simulations of galaxy evolution have shown that spiral arms play a crucial role in maintaining the disk's structure. Without the density waves, the disk would be more uniform, with star formation spread evenly throughout. The spiral arms concentrate star formation into specific regions, creating the beautiful patterns we see in spiral galaxies. Fact 23. The spiral pattern rotates more slowly than the stars. One of the most counterintuitive aspects of spiral arms is that the pattern rotates at a different speed than the stars and gas. The stars orbit the galaxy at speeds determined by the gravitational pull of the galaxy's mass, which decreases with distance from the center. But the spiral pattern, the density wave, rotates at a constant angular velocity, meaning it takes the same amount of time to complete one rotation regardless of distance from the center. This difference in rotation speeds is what allows the spiral pattern to persist. If the pattern rotated at the same speed as the stars, it would wind up tighter and tighter over time, eventually becoming a tightly wound spiral that would be unrecognizable. But because the pattern rotates more slowly, stars drift through it, entering from behind, slowing down as they pass through the arm, and then speeding up again as they exit the front. The pattern speed, the rate at which the spiral pattern rotates, is a key parameter in understanding the galaxy's dynamics. In the Milky Way, the pattern speed is estimated to be about 25 to 30 kilometers per second per kiloparsec, which means the pattern completes one rotation in about 200 to 300 million years. This is slower than the orbital speed of stars in the Sun's neighborhood, which is about 220 kilometers per second. There are special locations in the galaxy where the orbital speed of the stars matches the pattern speed. These are called corrosion resonances, and they're important for the stability of the spiral pattern. Inside the corrotation radius, stars orbit faster than the pattern, so they catch up to the arms from behind. Outside the corrotation radius, stars orbit slower than the pattern, so the arms catch up to them from behind. The Sun is thought to be near the corrotation radius, which means we're moving at roughly the same speed as the spiral pattern. This has interesting implications. It means the Sun spends a relatively long time in the same spiral arm, because we're not drifting through the pattern as quickly as stars at other distances. Some scientists have speculated that this might have consequences for Earth's climate or the rate of mass extinctions, because spiral arms are regions of higher stellar density and more frequent supernovae. But the evidence for such effects is weak, and the idea remains controversial. Fact 24. Magnetic fields follow the spiral arms. The Milky Way has a magnetic field, and it's not uniform. It follows the spiral arms. The field is weak by terrestrial standards, only a few microgauss, about 1,000,000 times weaker than Earth's magnetic field, but it extends across the entire galaxy, and it plays an important role in the dynamics of the interstellar medium. The magnetic field is generated by the motion of charged particles, electrons and ions. As the gas orbits the galaxy, it drags the magnetic field lines with it, stretching and twisting them. The result is a field that's aligned with the spiral arms, running parallel to the arms in the disk. The magnetic field affects the behavior of gas and dust in the disk. It provides support against gravitational collapse, making it harder for molecular clouds to form stars. It also channels the flow of gas, guiding it along the field lines. In regions where the field is strong, gas can flow along the arms, feeding star formation in the spiral arms. The magnetic field also affects cosmic rays, high-energy particles, mostly protons, that zip through the galaxy at nearly the speed of light. Cosmic rays are produced in supernova explosions and other energetic events, and they're accelerated to enormous energies by shock waves and magnetic fields. The galactic magnetic field traps cosmic rays, confining them to the disk and preventing them from escaping into intergalactic space. Astronomers study the galactic magnetic field using several techniques. One is to observe the polarization of starlight. Dust grains in the interstellar medium are elongated, and they tend to align with the magnetic field. When starlight passes through the dust, it becomes polarized, and the direction of polarization reveals the orientation of the field. Another technique is to observe the synchrotron radiation emitted by cosmic rays spiraling around magnetic field lines. This radiation is strongest in regions where the field is strong, such as the spiral arms. The magnetic field is a key ingredient in models of galaxy evolution. It affects the rate of star formation, the structure of the interstellar medium, and the propagation of cosmic rays. Understanding the field is essential for understanding how galaxies work. Fact 25. The spiral arms may be transient features despite their prominence. Spiral arms may not be permanent features of the galaxy. Some models suggest that the arms are transient. They form, persist for a while, and then dissolve, only to be replaced by new arms. This is in contrast to the density wave theory, which suggests that the arms are long-lived, quasi-steady structures. The transient spiral arm theory is based on computer simulations of galaxy evolution. These simulations show that spiral arms can form spontaneously from gravitational instabilities in the disk. As the disk rotates, small perturbations in the density can grow, creating spiral patterns. But these patterns are not stable. They change over time, with arms forming, merging, and dissolving in a complex dance. In this view, the spiral arms we see today are just one snapshot of a constantly evolving structure. The arms we see now may not be the same arms that existed 1 billion years ago, and they may not be the same arms that will exist 1 billion years from now. The galaxy is not a static object. It's a dynamic, living system, constantly reshaping itself. The debate between the density wave theory and the transient spiral arm theory is ongoing. Both models have strengths and weaknesses, and the truth may lie somewhere in between. It's possible that the Milky Way has both long-lived density waves and transient features, with the density waves providing a stable backbone and the transient features adding complexity and variability. Resolving this debate will require better observations of the galaxy's structure and dynamics, particularly in the outer regions where the spiral arms are less well studied. Missions like Gaia, which is mapping the positions and motions of billions of stars, are providing the data needed to test these models and refine our understanding of the Milky Way's spiral structure. At the heart of our galaxy lies something extraordinary. Hidden behind thick veils of dust, 26,000 light-years from Earth, the galactic center is a place of extremes. Here, gravity warps space and time. Stars orbit at speeds that would tear apart anything less massive. And at the very center, lurking in absolute darkness, is a monster, a supermassive black hole, 4 million times more massive than the Sun. We cannot see this region with ordinary telescopes. Visible light is blocked by dust clouds that fill the galactic disk, but infrared and radio waves pass through the dust, revealing a realm unlike anywhere else in the galaxy. Tonight we descend into the heart of the Milky Way. Fact 26. Sagittarius A is a supermassive black hole. At the exact center of the Milky Way sits Sagittarius A, pronounced Sagittarius A star, a supermassive black hole with a mass of approximately 4.1 million solar masses. This object is compact. Its event horizon, the point of no return, is only about 12 million miles across, roughly the size of Mercury's orbit. Yet it contains more mass than 4 million suns. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when massive objects collapse under their own gravity, compressing matter into an infinitely small point called a singularity. Sagittarius A didn't form from a single collapsing star. It grew over billions of years by consuming gas, dust, and stars that wandered too close. We've known about Sagittarius A since the 1970s, when radio astronomers detected a compact, bright radio source at the galactic center. But proving it was a black hole required decades of painstaking observations. Breakthrough came from tracking the orbits of stars near the center. These stars move at incredible speeds. Some orbit the black hole in less than 20 years, reaching velocities of up to 5,000 miles per second. By measuring their orbits, astronomers calculated the mass of the invisible object they're orbiting. The only explanation is a supermassive black hole. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, showing a glowing ring of hot gas surrounding a dark central shadow, the black hole's silhouette against the background light. It was direct visual proof of what astronomers had long suspected. Fact 27. The black hole is currently quiet despite its enormous mass. Sagittarius A is surprisingly quiet. It's not actively feeding on large amounts of material, so it doesn't shine brightly like the supermassive black holes in some other galaxies. Those active black holes, called quasars, can outshine entire galaxies as they consume vast quantities of gas and dust. Sagittarius A, by contrast, is dormant, sipping only small amounts of material. This wasn't always the case. Evidence suggests that the galactic center was much more active in the past. X-ray observations have revealed giant bubbles of hot gas extending above and below the galactic disk, the Fermi bubbles, which may have been created by a massive outburst from Sagittarius A few million years ago. During that event, the black hole may have consumed a large cloud of gas or even a cluster of stars. The black hole's current quietness is fortunate for us. If it were actively feeding, it would emit intense radiation that could affect the entire galaxy, potentially stripping away the atmospheres of planets and disrupting star formation. Instead, Sagittarius A sits in relative silence, a sleeping giant at the galaxy's heart. Fact 28. Stars orbit the black hole at extreme speeds. The stars closest to Sagittarius A move faster than any other stars in the galaxy. Astronomers have been tracking these stars for over 25 years, watching them complete their orbits around the invisible black hole. One star, called S2, or S02, has been particularly well studied. S2 is a blue main sequence star about 15 times more massive than the Sun. Its orbit brings it as close as 11 billion miles from the black hole, closer than Neptune is to the Sun. At its closest approach, S2 reaches speeds of about 5,000 miles per second, or nearly 3% the speed of light. At that velocity, the star experiences significant relativistic effects. Time slows down for the star relative to distant observers, and its light is redshifted by the black hole's intense gravity. These observations have allowed astronomers to test Einstein's theory of general relativity in one of the most extreme gravitational environments known. The theory predicts that S2's orbit should precess. The ellipse should slowly rotate over time. Observations have confirmed this precession, matching Einstein's predictions with remarkable precision. Other stars orbit even closer. S62, discovered more recently, has an orbital period of only 9.9 years and comes within 9 billion miles of the black hole. These stars are living on the edge, dancing around a gravitational abyss that could swallow them if they strayed just a bit closer. Fact 29. The galactic center contains millions of stars in a small volume. The region around Sagittarius A is extraordinarily crowded. Within just a few light years of the black hole, there are millions of stars packed together. This is a stellar density thousands of times higher than in the Sun's neighborhood. If Earth were located there, the night sky would be ablaze with stars brighter than Venus, and there would be no true darkness. Most of these stars are old red giants and smaller main sequence stars. But there are also young, massive stars, hot blue giants that shouldn't exist so close to the black hole. Star formation requires cold, dense gas clouds, but the environment near the black hole is too hot and turbulent for normal star formation. The presence of these young stars is a puzzle. One theory is that they formed farther out and then migrated inward, perhaps in a dense star cluster that was disrupted by the black hole's gravity. Another possibility is that they formed in a massive accretion disk around the black hole in a brief period when the black hole was actively feeding. The mystery remains unsolved. The high stellar density has consequences. Close encounters between stars are common, and some stars are ejected from the galactic center at high speeds, becoming hypervelocity stars that can escape the galaxy entirely. Others are torn apart by tidal forces or consumed by the black hole. Fact 30. The galactic center is obscured by 25 magnitudes of dust extinction 1. Of the biggest challenges in studying the galactic center is the dust. Between us and the center lie thick clouds of interstellar dust that absorb and scatter light. This dust causes what astronomers call extinction, the dimming of light as it passes through the dust. At the galactic center, the extinction is about 25 magnitudes in visible light. A magnitude is a logarithmic measure of brightness, and 25 magnitudes corresponds to a factor of 10 billion. In other words, visible light from the galactic center is dimmed by a factor of 10 billion by the time it reaches us. This makes the center completely invisible to optical telescopes. Fortunately, infrared light penetrates dust much more effectively than visible light. At infrared wavelengths, the extinction drops to only a few magnitudes, making it possible to see through the dust and observe the stars and gas near the black hole. Radio waves pass through the dust even more easily, allowing astronomers to map the structure of the galactic center in exquisite detail. This is why the first observations of Sagittarius A were made at radio wavelengths, and why the detailed studies of stellar orbits near the black hole use infrared telescopes. Without these longer wavelengths, the galactic center would remain hidden from us, a mystery we could never solve. Fact 31. The central parsec contains a dense nuclear star cluster, the innermost region of the galaxy. Within about 1 parsec, 3.26 light-years of Sagittarius A, is occupied by a nuclear star cluster, a dense, spherical collection of stars gravitationally bound to the black hole. This cluster contains about 25 million solar masses of stars, making it one of the most massive star clusters in the galaxy. Nuclear star clusters are common in galaxies. Most galaxies with a central bulge have one, and they're thought to form through a combination of star formation near the black hole and the infall of globular clusters from the surrounding galaxy. The Milky Way's nuclear star cluster is relatively modest compared to some, but it's still a remarkable structure. The cluster is dominated by old stars, but it also contains the young, massive stars mentioned earlier. The mix of old and young stars suggests a complex history of star formation and dynamical evolution. The cluster's gravity helps stabilize the orbits of stars near the black hole, preventing them from being ejected or consumed too quickly. Studying the nuclear star cluster helps astronomers understand how supermassive black holes and their host galaxies co-evolve. There's a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge, suggesting that the two grow together over cosmic time. The nuclear star cluster is part of this relationship. Fact 32. Radio filaments extend from the galactic center. One of the strangest features of the galactic center is the presence of long, thin filaments of radio emission. These filaments are dozens of light-years long, but only a fraction of a light-year wide, and they extend perpendicular to the galactic plane. They were discovered in the 1980s and remain poorly understood. The filaments emit synchrotron radiation, light produced by electrons spiraling around magnetic field lines at nearly the speed of light. This suggests that the filaments are threaded by strong magnetic fields, much stronger than the average field in the galaxy. The electrons must be accelerated to high energies by some process, possibly shock waves or magnetic reconnection events. The origin of the filaments is unclear. They may be related to past activity of Sagittarius A, or they may be produced by the collective effects of stellar winds and supernova explosions in the dense central region. Some filaments appear to be connected to supernova remnants or molecular clouds, while others seem to float freely in space. The filaments are a reminder that the galactic center is not just a collection of stars orbiting a black hole. It's a complex active environment with strong magnetic fields, energetic particles, and processes we're only beginning to understand. Fact 33. The Fermi bubbles extend 25,000 light-years above and below the disk in 2010. Astronomers using the Fermi Gamma Ray Space Telescope discovered 2 enormous bubbles of high-energy gamma rays extending above and below the galactic center. These Fermi bubbles are huge. Each one stretches about 25,000 light-years from the galactic plane, making them comparable in size to the galaxy's disk. The bubbles are filled with hot gas and cosmic rays, and they emit gamma rays, the highest energy form of light. Their edges are sharp and well-defined, suggesting they were created by a sudden, powerful event rather than a gradual process. The most likely explanation is that the bubbles were inflated by a massive outburst from Sagittarius A a few million years ago. During this outburst, the black hole may have consumed a large amount of gas, releasing enormous amounts of energy in the form of jets and winds. These jets punched through the disk and inflated the bubbles, sweeping up gas and accelerating cosmic rays. Alternatively, the bubbles could have been created by a burst of star formation in the galactic center, with thousands of supernovae exploding in a short period and driving a galactic wind. Either way, the Fermi bubbles are evidence of a violent event in the galaxy's recent past. Fact 34. Molecular clouds near the center are heated to extreme temperatures. The gas near the galactic center is not cold and quiescent like the molecular clouds in the spiral arms. It's hot, turbulent, and irradiated by intense radiation from the dense population of stars. Temperatures in some regions reach thousands of degrees, far too hot for normal star formation. Despite the heat, there are still molecular clouds near the center. These clouds are denser and more massive than typical clouds in the disk, and they're held together by the strong gravitational field of the central black hole and the surrounding stars, but they're also being torn apart by tidal forces and heated by radiation, creating a chaotic dynamic environment. Some of these clouds are on collision courses with Sagittarius A. Astronomers have observed clouds falling toward the black hole, stretched into long filaments by tidal forces. One such cloud, called G2, was predicted to collide with the black hole in 2014. Astronomers watched eagerly, hoping to see a dramatic flare as the cloud was consumed. But the event was anticlimactic. The cloud survived, suggesting it may have been a star surrounded by a dusty envelope rather than a pure gas cloud. Fact 35. The galactic center has a strong magnetic field. The magnetic field at the galactic center is much stronger than in the rest of the galaxy. Measurements suggest field strengths of up to a few milligauss, about 1,000 times stronger than the average field in the disk. This strong field plays a crucial role in the dynamics of gas near the black hole. The field channels the flow of gas, guiding it along field lines and preventing it from falling directly into the black hole. This may explain why Sagittarius A is so quiet. The magnetic field acts as a barrier, throttling the rate at which gas can be accreted. Only when the field is disrupted, perhaps by a passing star or cloud, can gas fall in and feed the black hole. The strong field also accelerates particles to high energies, creating cosmic rays and producing the synchrotron radiation observed in the radiofilaments. The field is likely generated by the motion of the hot ionized gas in the central region, amplified by turbulence and shear. Fact 36. Hypervelocity stars are ejected from the galactic center. Some stars near the galactic center are ejected at such high speeds that they can escape the galaxy entirely. These hypervelocity stars are traveling at speeds of 1,000 kilometers per second or more, fast enough to break free from the Milky Way's gravitational pull. The mechanism for ejecting these stars involves close encounters with the supermassive black hole. If a binary star system passes close to Sagittarius A, the black hole's gravity can tear the binary apart. One star is captured into a tight orbit around the black hole, while the other is flung outward at high speed, carrying away the orbital energy of the binary. Dozens of hypervelocity stars have been discovered, most of them far from the galactic center, speeding through the halo on their way out of the galaxy. By tracing their trajectories backward, astronomers have confirmed that many originated near Sagittarius A. These stars are messengers from the galactic center, carrying information about the extreme environment there. Fact 37. The central black hole grows by consuming stars and gas. Sagittarius A didn't start out with a mass of 4 million suns. It grew over billions of years by accreting material, gas, dust, and occasionally entire stars. Every time something falls past the event horizon, the black hole's mass increases. The growth rate is slow now because the black hole is starved of material. It accretes only about 1,000th of a solar mass per million years. At this rate, it would take trillions of years to double its mass. But in the past, when the galaxy was younger and gas was more abundant, the black hole likely grew much faster. Occasionally, a star wanders too close and is torn apart by tidal forces in an event called a tidal disruption. The star is stretched into a long stream of gas, half of which falls into the black hole while the other half is ejected. These events produce bright flares of radiation, and astronomers have observed them in other galaxies. Sagittarius A may experience a tidal disruption every few thousand years. Fact 38. The galactic center may harbor thousands of stellar mass black holes. In addition to the supermassive black hole, the galactic center may contain thousands of smaller stellar mass black holes, the remnants of massive stars that exploded as supernova. These black holes, each with masses of a few to a few dozen solar masses, are invisible unless they're actively accreting gas or orbiting a companion star. Theoretical models predict that stellar mass black holes should sink toward the galactic center over time, pulled inward by a process called dynamical friction. As a black hole moves through the dense stellar environment, it gravitationally interacts with nearby stars, losing energy and spiraling inward. Over millions of years, thousands of black holes could accumulate near Sagittarius A. Recent observations have found evidence for this population. X-ray telescopes have detected faint X-ray sources near the galactic center that may be stellar mass black holes accreting gas. If confirmed, this would be the densest concentration of black holes anywhere in the galaxy, a graveyard of dead stars orbiting the supermassive black hole at the center. Stars are not eternal. They are born, they live, and they die. And the places where they are born are among the most beautiful in the galaxy. Vast clouds of gas and dust, glowing with the light of newborn suns. Tonight, we visit these stellar nurseries. Fact 39. Nebulae are clouds of gas and dust where stars form. Nebulae are the birthplaces of stars. These clouds contain hydrogen, helium, and trace amounts of heavier elements, along with tiny grains of dust. When a region of a nebula becomes dense enough, gravity takes over, pulling the gas inward. The cloud collapses, heats up, and eventually ignites nuclear fusion. A star is born. Fact 40. The Orion Nebula is the nearest major star-forming region. The Orion Nebula lies 1,350 light-years from Earth, making it the closest major stellar nursery. Visible to the naked eye as a fuzzy patch in Orion's sword, it's actually a vast cloud of gas about 24 light-years across. Inside, thousands of young stars are forming. The brightest stars, called the trapezium, illuminate the surrounding gas, making it glow in shades of red and green. Fact 41. The Carina Nebula contains some of the galaxy's most massive stars. The Carina Nebula, 7,500 light-years away, is one of the largest and brightest nebulae in the sky. It's home to Eta Carinae, a star system over 100 times more massive than the Sun. This star is unstable, prone to violent outbursts. In the 1840s, it briefly became one of the brightest stars in the sky. Eta Carinae will likely explode as a supernova within the next million years. Fact 42. Protostars are infant stars still forming before a star ignites fusion. It exists as a protostar, a hot, dense core surrounded by a disk of gas and dust. Protostars are hidden inside their natal clouds, invisible in optical light. But they glow brightly in infrared. Over hundreds of thousands of years, the protostar accumulates mass from the surrounding disk. When the core reaches about 10 million degrees, hydrogen fusion begins, and the star is born. Fact 43. Stellar winds and radiation sculpt nebulae young. Massive stars produce intense ultraviolet radiation and powerful stellar winds. This energy carves the surrounding nebula into intricate shapes, pillars, bubbles, and cavities. The radiation ionizes the gas, causing it to glow. The winds push gas away, creating expanding shells. Over time, the nebula is dispersed, and the stars drift apart. Fact 44. The pillars of creation are being destroyed by starlight. The pillars of creation in the Eagle Nebula are iconic, but they're being eroded. The intense radiation from nearby young stars is evaporating the gas, slowly eating away at the pillars. Dense clumps resist the erosion longer, creating the pillar shapes. Inside these clumps, new stars are forming, even as the pillars themselves are destroyed. Fact 45. How eye regions are zones of ionized hydrogen. When ultraviolet light from hot stars strikes hydrogen gas, it strips away electrons, ionizing the atoms. The result is an HII region, a glowing bubble of ionized hydrogen. These regions emit a characteristic red light as electrons recombine with protons. HII regions mark the locations of massive young stars and are among the brightest features of spiral galaxies. Fact 46. The Lagoon Nebula contains a bright HII region. The Lagoon Nebula, 4,000 light-years away in Sagittarius, is a stellar nursery bisected by a dark dust lane. At its heart is an HII region powered by several hot young stars. The nebula glows red from hydrogen emission and appears as a bright patch visible to the naked eye under dark skies. It's a favorite target for astrophotographers. Fact 47. Dark nebulae are dense clouds that block background light. Not all nebulae glow. Dark nebulae are dense clouds of gas and dust that block the light from stars behind them, appearing as dark patches against the Milky Way. The Horsehead Nebula and the Coalsack Nebula are famous examples. These clouds are cold and dense, ideal conditions for star formation. Many dark nebulae are future stellar nurseries. Fact 48. Bok globules are small, dense clouds where stars form. Bok globules are small, dark clouds, typically less than a light-year across. They're named after astronomer Bart Bok, who studied them in the 1940s. These globules are dense and cold, and many contain protostars. They appear as dark spots against bright nebulae, like drops of ink on glowing paper. Bok globules are stellar cocoons. Fact 49. Herbig-Haro objects are jets from young stars. Young stars don't just pull in gas, they also eject it. Herbig-Haro objects are bright patches of nebulosity created when jets of gas from a protostar slam into the surrounding cloud at hundreds of miles per second. The collision creates shock waves that heat the gas, making it glow. These jets help the protostar shed angular momentum, allowing it to continue accreting mass. Fact 50. Reflection nebulae scatter starlight. Some nebulae don't emit their own light, they reflect it. Reflection nebulae are clouds of dust that scatter light from nearby stars, appearing blue because blue light scatters more efficiently than red. The Pleiades star cluster is surrounded by a faint reflection nebula. These nebulae are often found near young star clusters. Fact 51. Planetary nebulae are the remnants of dying stars despite their name. Planetary nebulae have nothing to do with planets. They're shells of gas ejected by dying stars. When a sun-like star exhausts its fuel, it sheds its outer layers, creating an expanding shell. The hot core, now exposed, ionizes the gas, making it glow. The Rin Nebula and the Helix Nebula are famous examples. These nebulae last only tens of thousands of years before fading away. For thousands of years, humanity wondered, are there other worlds like Earth? Do other stars have planets? The answer came only recently. In 1995, astronomers discovered the first planet orbiting a sun-like star beyond our solar system. Since then, we've found thousands more. The Milky Way is filled with planets, billions of them, orbiting distant suns. Fact 52. Over 5,000 exoplanets have been confirmed as of now. Astronomers have confirmed more than 5,000 planets orbiting other stars. These exoplanets range from gas giants larger than Jupiter to rocky worlds smaller than Earth. Each discovery adds to our understanding of how planetary systems form and evolve. The count grows every year as new detection methods improve and more data is analysed. Most of these planets were found using NASA's Kepler Space Telescope. which monitored hundreds of thousands of stars for years. The diversity is staggering. Hot Jupiters orbiting closer to their stars than Mercury, super-Earths with no analogue in our solar system, and ice giants in distant orbits. Fact 53. Most stars in the Milky Way have planets. Planets are not rare. Statistical studies suggest that nearly every star in the galaxy hosts at least one planet. This means there are likely hundreds of billions of planets in the Milky Way. Some stars have multiple planets, forming complex systems like our own. The realization that planets are common has transformed our view of the galaxy. We are not unique. Planetary systems are a natural outcome of star formation, arising from the disks of gas and dust that surround young stars. Fact 54. The transit method detects planets by measuring starlight dips. Most exoplanets are found using the transit method. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of the star's light. By measuring this dip in brightness, astronomers can detect the planet and determine its size. The amount of light blocked depends on the planet's radius. Larger planets block more light. Repeated transits reveal the planet's orbital period. This method works best for planets in close orbits around their stars where transits are frequent. Kepler used this technique to discover thousands of planets. Fact 55. The radial velocity method detects planets by stellar wobble. Stars don't stay perfectly still, they wobble slightly due to the gravitational pull of their orbiting planets. This wobble causes the star's light to shift in wavelength, alternating between redshift and blueshift as the star moves toward and away from us. By measuring these shifts, astronomers can detect planets and estimate their masses. This radial velocity method was used to discover the first exoplanet around a Sun-like star, 51 Pegasi b, in 1995. It's most sensitive to massive planets in close orbits, which produce the largest wobbles. Fact 56. Hot Jupiters are gas giants orbiting close to their stars. One of the most surprising discoveries was hot Jupiters, gas giants orbiting extremely close to their stars, often closer than Mercury is to the Sun. These planets have surface temperatures exceeding 1,000 degrees Celsius, hot enough to vaporize metals. They shouldn't exist according to early planet formation theories, which predicted gas giants would form far from their stars where it's cold. The explanation is migration. These planets formed farther out and then spiraled inward due to interactions with the protoplanetary disk. Hot Jupiters are tidally locked, with one side always facing their star. Fact 57. Super-Earths are rocky planets larger than Earth. Super-Earths are planets with masses between Earth and Neptune, typically 2 to 10 times Earth's mass. Many are rocky with solid surfaces, though some may have thick atmospheres or even water oceans. Our solar system has no super-Earths, yet they're among the most common planets in the galaxy. Their compositions and climates remain mysterious. Some orbit in their star's habitable zone, the region where liquid water could exist on the surface. Whether super-Earths can support life is unknown, but they're prime targets in the search for habitable worlds. Fact 58. The habitable zone is where liquid water can exist. The habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star where a planet's surface temperature allows liquid water to exist. Too close, and water evaporates. Too far, and it freezes. The exact boundaries depend on the star's temperature and the planet's atmosphere. Earth sits comfortably in the Sun's habitable zone. Dozens of exoplanets have been found in habitable zones around other stars. This doesn't guarantee they're habitable. Factors like atmospheric composition, magnetic fields, and stellar activity also matter, but it's a promising start. Fact 59. Proxima Centauri b is the nearest known exoplanet. The closest exoplanet to Earth orbits Proxima Centauri, a red dwarf star just 4.2 light-years away. Proxima Centauri b is a rocky planet with a mass slightly larger than Earth's. It orbits within its star's habitable zone, completing one orbit every 11 days. However, Proxima Centauri is an active star, producing frequent flares that bombard the planet with radiation. Whether Proxima b could support life is uncertain. Its proximity makes it a prime target for future study, including potential interstellar missions. If we ever send a probe to another star system, Proxima Centauri is the most likely destination. Fact 60. TRAPPIST. One has 7 Earth-sized planets. The TRAP. PIST, one system 40 light-years away, is remarkable. It contains 7 Earth-sized planets orbiting an ultra-cool red dwarf star. 3 of these planets orbit in the habitable zone. The planets are tightly packed. Their orbits are closer together than the inner planets of our solar system. They likely experience strong tidal forces and may be tidally locked. Some could have atmospheres and liquid water. The TASAP. PIST, one system is one of the best laboratories for studying potentially habitable worlds. Future telescopes like the James Webb Space Telescope are analyzing their atmospheres for signs of water, oxygen, or other biosignatures. Fact 61. Rogue planets drift through the galaxy without stars. Rogue planets, also called free-floating planets, drift through the galaxy alone. They were either ejected from their original solar systems by gravitational interactions or formed independently in interstellar space. Estimates suggest there may be billions of rogue planets in the Milky Way, possibly outnumbering stars. These planets are difficult to detect because they emit no light of their own. Some have been found through gravitational microlensing, where the planet's gravity briefly magnifies the light of A. Fact 62. Some exoplanets orbit binary star systems. Many stars are not alone. They exist in binary or multiple star systems. Some planets orbit both stars in a binary system, experiencing sunrises and sunsets from 2 suns, like Tatooine in Star Wars. These circumbinary planets are stable despite the complex gravitational environment. Others orbit just one star in a binary system, with the second star appearing as a bright point in the sky. The dynamics of planet formation in binary systems are complex, but planets manage to form and survive. Kepler discovered several circumbinary planets, proving that planetary systems can be more diverse than we imagined. Fact 63. Exoplanet atmospheres can be analyzed using spectroscopy. When a planet transits its star, some starlight passes through the planet's atmosphere. Different gases absorb light at specific wavelengths, leaving signatures in the spectrum. By analyzing this transmitted light, astronomers can identify the atmospheric composition. Water vapor, methane, carbon dioxide, and other molecules have been detected in exoplanet atmospheres. This technique, called transmission spectroscopy, is one of the most powerful tools for studying distant worlds. The James Webb Space Telescope is revolutionizing this field, detecting molecules that were previously impossible to observe. Finding oxygen or methane in the right combination could indicate biological activity. Fact 64. The search for biosignatures focuses on atmospheric chemistry. The ultimate goal of exoplanet research is to find signs of life. Biosignatures are chemical indicators that life might be present. Oxygen is a strong biosignature because it's highly reactive and would disappear from an atmosphere without constant replenishment by life. Methane combined with oxygen is even more compelling as these gases react with each other and shouldn't coexist unless something is producing them. Other potential biosignatures include phosphine, nitrous oxide, or unusual ratios of atmospheric gases. Detecting biosignatures won't prove life exists, but it would be the strongest evidence we could obtain from a distance. The search continues. Fact 65. Dark matter makes up about 85% of the galaxy's mass. The Milky Way contains roughly 1.5 trillion solar masses of material, but only about 200 billion solar masses are in the form of stars, gas, and dust, the ordinary matter we can see. The remaining 1.3 trillion solar masses are dark matter. This invisible substance dominates the galaxy's mass budget, outweighing ordinary matter by a factor of 6 to 1. We cannot see dark matter directly, but its gravitational effects are unmistakable. It holds the galaxy together, preventing stars from flying apart as the galaxy rotates. Without dark matter, the Milky Way as we know it could not exist. Fact 66. Dark matter was discovered through galaxy rotation curves. The first evidence for dark matter came from studying how galaxies rotate. In the 1970s, astronomer Vera Rubin measured the velocities of stars at different distances from the centers of spiral galaxies. She expected stars farther out to orbit more slowly, just as outer planets in the solar system orbit more slowly than inner planets. Instead, she found that stars in the outer regions moved just as fast as those closer in. This flat rotation curve could only be explained if galaxies contained far more mass than we could see. The extra mass, dark matter, extends far beyond the visible disk, forming a massive halo. Fact 67. The dark matter halo extends far beyond the visible galaxy. The Milky Way's dark matter halo is enormous. It extends at least 200,000 light-years from the galactic center, and possibly much farther, perhaps 500,000 light-years or more. This dwarfs the visible disk, which is only 100,000 light-years across. The halo is roughly spherical, enveloping the entire galaxy in a cocoon of invisible mass. The density of dark matter decreases with distance from the center, but even in the outer halo, dark matter dominates over ordinary matter. The Sun, as it orbits the galaxy, is moving through this dark matter halo, though we cannot detect the particles directly. Fact 68. We don't know what dark matter is made of. Despite decades of research, we still don't know what dark matter is. It's not made of atoms or any particles in the standard model of particle physics. Leading candidates include WIMPs, weakly interacting massive particles, axions and sterile neutrinos, hypothetical particles that interact only through gravity and possibly the weak nuclear force. Experiments around the world are searching for dark matter particles, using detectors deep underground to shield them from cosmic rays. So far, no direct detection has been confirmed. Dark matter remains one of the greatest mysteries in physics. Fact 69. Gravitational lensing reveals dark matter's distribution. One way to map dark matter is through gravitational lensing. Massive objects bend space-time, causing light from distant sources to curve as it passes by. This effect, predicted by Einstein's general relativity, allows astronomers to see dark matter by observing how it distorts the light from background galaxies. By analyzing these distortions, astronomers can map the distribution of dark matter in and around galaxies. These maps show that dark matter forms a smooth, extended halo, consistent with predictions from computer simulations. Fact 70. Dark matter clumps may orbit within the halo. The dark matter halo is not perfectly smooth. Simulations predict it contains substructure, smaller clumps of dark matter orbiting within the larger halo. These clumps, called subhalos, are remnants of smaller dark matter halos that were absorbed as the Milky Way grew. Some subhalos may contain stars forming dwarf galaxies that orbit the Milky Way. Others may be entirely dark, invisible except through their gravitational effects. Detecting these dark subhalos is challenging, but they may reveal themselves through their gravitational influence on stellar streams or through gamma-ray emission if dark matter particles annihilate. Fact 71. Stellar streams trace the halo structure when a small galaxy or star cluster is torn apart by the Milky Way's gravity. Its stars are stretched into long streams that orbit the galaxy. These stellar streams trace the gravitational potential of the halo, providing clues about the distribution of dark matter. Dozens of stellar streams have been discovered, remnants of disrupted dwarf galaxies and globular clusters. By studying their shapes and velocities, astronomers can infer the mass and structure of the dark matter halo. Streams are sensitive to dark matter subhalos. A passing clump of dark matter can create gaps or kinks in a stream. Fact 72. The Milky Way's halo contains ancient globular clusters. Globular clusters orbit in the halo, relics from the galaxy's earliest days. These dense, spherical collections of stars are among the oldest objects in the Milky Way, with ages of 10 to 13 billion years. They formed when the galaxy was young, and they've been orbiting ever since, passing through the disk and back out into the halo on highly elliptical paths. The Milky Way has about 150 known globular clusters, but there may be more hidden behind the dust of the galactic disk. These clusters are laboratories for studying stellar evolution and the early history of the galaxy. Fact 73. High-velocity clouds are gas clouds falling into the galaxy. The halo is not empty. It contains clouds of neutral hydrogen gas, some of which are moving at high velocities relative to the disk. These high-velocity clouds are thought to be falling into the galaxy, accreted from the intergalactic medium, or stripped from satellite galaxies. When they collide with the disk, they can trigger star formation. Some high-velocity clouds may be primordial gas left over from the galaxy's formation, never incorporated into stars. Others are recycled gas ejected from the disk by supernova explosions and now falling back. Fact 74. The halo contains a hot gas corona surrounding the Milky Way, is a corona of hot diffuse gas, heated to temperatures of 1,000,000 degrees or more. This gas emits X-rays and is difficult to detect, but observations suggest it contains a significant amount of mass. The corona is thought to be the reservoir of baryonic matter, ordinary matter, that the galaxy draws upon for star formation. Gas from the corona cools and falls into the disk, replenishing the supply of raw material for new stars. The corona may also contain metals ejected from the disk by supernova-driven winds. Fact 75. Dark matter halos formed first in the early universe. In the early universe, dark matter began clumping together before ordinary matter. Because dark matter doesn't interact with light or itself, except through gravity, it could collapse freely under gravity while ordinary matter was still too hot and ionized to clump. These dark matter halos formed the gravitational wells into which ordinary matter later fell, forming the first stars and galaxies. The Milky Way's dark matter halo formed first, and the visible galaxy assembled within it. This hierarchical structure formation is a cornerstone of modern cosmology. Fact 76. The local group's dark matter dominates its dynamics. The local group, the collection of galaxies that includes the Milky Way and Andromeda, is dominated by dark matter. The total mass of the local group is about 2 to 3 trillion solar masses, most of it dark matter. The gravitational pull of this dark matter governs the motions of all the galaxies in the group. The Milky Way and Andromeda are moving toward each other, drawn by their mutual gravitational attraction, which is dominated by their dark matter halos. When they collide in about 4.5 billion years, their dark matter halos will merge first, followed by their stars and gas. Fact 77. Dark matter may interact with itself in unknown ways, while dark matter doesn't interact with ordinary matter except through gravity. It may interact with itself in ways we don't yet understand. Some models propose that dark matter particles can collide and annihilate, producing gamma rays or other particles. Others suggest dark matter may have its own dark forces, analogous to electromagnetism but acting only on dark matter. These self-interactions could affect the structure of dark matter halos, creating cores instead of the dense cusps predicted by standard models. Observations of dwarf galaxies and galaxy clusters are testing these ideas, but the nature of dark matter remains elusive. Fact 78. The Milky Way has cannibalized smaller galaxies. The Milky Way grew by eating its neighbors. Throughout its history, it has absorbed dozens of smaller galaxies that wandered too close. These mergers added stars to the halo and disk, and they left behind streams of stars that trace the paths of the devoured galaxies. Astronomers have identified the remnants of several past mergers, including the Sagittarius Dwarf Elliptical Galaxy, which is currently being torn apart by the Milky Way's gravity. Its stars are spread in long streams that wrap around the galaxy multiple times. Each merger adds mass and complexity to the Milky Way structure. Fact 79. The Sagittarius Dwarf Galaxy is being torn apart. The Sagittarius Dwarf Elliptical Galaxy is one of the Milky Way's closest satellite galaxies, located about 70,000 light-years from Earth. It's being pulled apart by tidal forces, stretched into long streams of stars that orbit the galaxy. The dwarf galaxy has already made several passes through the Milky Way's disk, and each passage strips away more stars. Eventually, it will be completely dissolved, its stars absorbed into the Milky Way's halo. The Sagittarius stream is one of the most prominent stellar streams in the sky, visible in surveys that map the positions of millions of stars. Fact 80. The Gaia-Enceladus merger occurred 10 billion years ago. About 10 billion years ago, the Milky Way collided with a dwarf galaxy called Gaia-Enceladus. This was one of the most significant mergers in the galaxy's history. The collision added about 50 billion solar masses of stars and dark matter to the Milky Way, and it disrupted the disk, thickening it and heating the stellar orbits. The remnants of Gaia-Enceladus are now scattered throughout the halo, but astronomers have identified them by their distinctive chemical compositions and orbital patterns. This ancient merger shaped the structure of the galaxy we see today. Fact 81. The Large and Small Magellanic Clouds are satellite galaxies. The Large and Small Magellanic Clouds are two dwarf galaxies that orbit the Milky Way. They're visible to the naked eye from the southern hemisphere, appearing as faint cloudy patches. The Large Magellanic Cloud is about 160,000 light-years away and contains about 10 billion stars. The Small Magellanic Cloud is slightly farther and smaller. Both galaxies are being distorted by the Milky Way's gravity, and they're connected by a bridge of gas stripped from their outer regions. In a few billion years, they may be absorbed into the Milky Way. Fact 82. The Magellanic Stream is a trail of gas. The Magellanic Clouds are leaving a trail. As they orbit the Milky Way, tidal forces and ram pressure from the galactic halo strip gas from them, creating the Magellanic Stream, a ribbon of neutral hydrogen gas stretching across more than 100 degrees of the sky. The stream contains about 200 million solar masses of gas, and it's falling toward the Milky Way. When it collides with the disk in about 200 million years, it will trigger a burst of star formation. The stream is evidence of the ongoing interaction between the Milky Way and its satellites. Fact 83. Andromeda is approaching at 110 kilometers per second. The Andromeda Galaxy, also known as M31, is the nearest large spiral galaxy, located about 2.5 million light-years from the Milky Way. It's moving toward us at about 110 kilometers per second. This might sound fast, but at such a vast distance, it will take about 4.5 billion years for the two galaxies to collide. Andromeda is slightly larger than the Milky Way, containing about 1 trillion stars compared to our few hundred billion. The collision is inevitable, driven by the mutual gravitational attraction of the two galaxies and their dark matter halos. Fact 84. The Milky Way-Andromeda collision will occur in 4.5 billion years In about 4.5 billion years, the Milky Way and Andromeda will collide. The first encounter will be a close pass, with the two galaxies swinging around each other. Their gravitational interaction will distort both galaxies, pulling out long tidal tails of stars and gas. After the first pass, the galaxies will separate, but gravity will pull them back together. They'll collide again and again, each time losing energy and spiraling closer. Eventually, after several billion years, they'll merge into a single larger galaxy. Astronomers have nicknamed this future galaxy Milky Way. Fact 85. During the collision, stars rarely collide despite the violence of a galactic collision. Individual stars rarely collide with each other. Stars are tiny compared to the vast distances between them. Even in the densest parts of a galaxy, stars are separated by light years. When two galaxies merge, their stars pass by each other like two swarms of bees interpenetrating. The galaxies' shapes are distorted by gravity, and stellar orbits are scrambled, but actual stellar collisions are extremely rare. The gas, however, does collide, creating shock waves that trigger intense bursts of star formation. Fact 86. The collision will trigger massive star formation. When the Milky Way and Andromeda collide, their gas clouds will slam into each other at high velocities. These collisions will compress the gas, triggering gravitational collapse and igniting a starburst, a period of intense star formation. Millions of new stars will be born in a relatively short time, lighting up the merged galaxy with brilliant blue light. Many of these stars will be massive and short-lived, quickly dying in supernova explosions. The starburst will eventually exhaust the available gas and star formation will decline. The merged galaxy will settle into a more quiescent state. Fact 87. The merged galaxy will likely be an elliptical galaxy after the merger. The combined galaxy will no longer be a spiral. The collision will scramble the ordered rotation of the disks, and the stars will end up on random chaotic orbits. The result will be an elliptical galaxy, a smooth, featureless ball of stars with little gas and no ongoing star formation. Elliptical galaxies are common in the universe, and many are thought to form through mergers of spiral galaxies. The future Milky Way will be a giant elliptical, containing the combined stars of both the Milky Way and Andromeda, slowly aging as its stars burn out. Fact 88. The supermassive black holes will merge. Both the Milky Way and Andromeda have supermassive black holes at their centers. When the galaxies merge, these black holes will eventually sink to the center of the new galaxy and merge into a single, even more massive black hole. The merger will release enormous amounts of energy in the form of gravitational waves, ripples in space-time predicted by Einstein's general relativity. These waves will propagate across the universe at the speed of light. The merged black hole will have a mass of about 100 million solar masses, and it may briefly become an active galactic nucleus, shining brightly as it accretes gas. Fact 89. Earth will likely survive the collision. Despite the dramatic changes to the galaxy, Earth and the solar system will likely survive the collision unscathed. The Sun will be flung into a different orbit, possibly ending up in the outer regions of the merged galaxy, or even in a tidal tail. But the chances of a close encounter with another star are extremely small. The solar system will remain intact, and life on Earth, if it still exists, will witness a spectacular show. The night sky will be transformed, with Andromeda growing larger and larger until it fills the sky, and new stars blazing to life in the starburst regions. Fact 90. Other local group galaxies will be affected. The Milky Way-Andromeda collision will affect the entire local group. Smaller galaxies like the Triangulum Galaxy and the various dwarf galaxies will be pulled in by the gravitational chaos. Some may be absorbed into the merged galaxy, while others may be flung out into intergalactic space. The local group as we know it will cease to exist. replaced by a single dominant elliptical galaxy surrounded by a few scattered survivors. The collision will reshape the local cosmic landscape, creating a new structure from the remnants of the old. Fact 91. The Milky Way has enriched the universe with heavy elements. When the universe began, it contained only hydrogen, helium, and trace amounts of lithium. Every other element, carbon, oxygen, iron, gold, was created inside stars. Nuclear fusion in stellar cores builds heavier elements from lighter ones, and when stars die, they scatter these elements into space. Supernovae are particularly important, producing elements heavier than iron in their violent explosions. Over billions of years, the Milky Way has enriched the interstellar medium with heavy elements, raising the metallicity of each new generation of stars. The Sun contains far more heavy elements than the oldest stars in the galaxy, and planets like Earth could not exist without this enrichment. Fact 92. Supernovae recycle material back into the interstellar medium. When a massive star exhausts its fuel, it collapses and explodes as a supernova, releasing as much energy in a few seconds as the Sun will emit in its entire lifetime. The explosion ejects the star's outer layers into space at speeds of thousands of kilometers per second. This material, enriched with heavy elements, mixes with the interstellar medium and becomes part of future generations of stars and planets. Supernovae also create shockwaves that compress nearby gas clouds, triggering new star formation. The cycle of stellar birth, death, and rebirth is the engine that drives the galaxy's evolution. Fact 91. The Milky Way has enriched the universe with heavy elements. When the universe began, it contained only hydrogen, helium, and trace amounts of lithium. Every other element, carbon, oxygen, iron, gold, was created inside stars. Nuclear fusion in stellar cores builds heavier elements from lighter ones, and when stars die, they scatter these elements into space. Supernovae are particularly important, producing elements heavier than iron in their violent explosions. Over billions of years, the Milky Way has enriched the interstellar medium with heavy elements, raising the metallicity of each new generation of stars. The Sun contains far more heavy elements than the oldest stars in the galaxy, and planets like Earth could not exist without this enrichment. Fact 92. Supernovae recycle material back into the interstellar medium. When a massive star exhausts its fuel, it collapses and explodes as a supernova, releasing as much energy in a few seconds as the Sun will emit in its entire lifetime. The explosion ejects the star's outer layers into space at speeds of thousands of kilometers per second. This material, enriched with heavy elements, mixes with the interstellar medium and becomes part of future generations of stars and planets. Supernovae also create shockwaves that compress nearby gas clouds, triggering new star formation. The cycle of stellar birth, death, and rebirth is the engine that drives the galaxy's evolution. Fact 93. Red giants will eventually dominate the galaxy. As the Milky Way ages, its stellar population changes. Massive stars live fast and die young, burning out in only a few million years. Lower mass stars like the Sun live much longer, and the smallest red dwarfs can live for trillions of years. Over time, the massive stars will all die, and the galaxy will be dominated by red giants, white dwarfs, and red dwarfs. Star formation will slow as the galaxy exhausts its gas supply. Eventually, billions of years from now, the Milky Way will become a quiet, aging galaxy, filled with the fading embers of long-dead stars. Fact 94. The Sun will become a red giant in 5 billion years. The Sun is currently middle-aged, about 4.6 billion years old. In another 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium. This will cause the Sun to expand into a red giant, swelling to hundreds of times its current size. It will likely engulf Mercury and Venus, and possibly Earth. The outer layers of the Sun will be ejected into space, forming a planetary nebula, while the core will collapse into a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. The Sun's death will mark the end of the solar system as we know it. Fact 95. White dwarfs are the remnants of Sun-like stars. When stars like the Sun die, they leave behind white dwarfs, hot, dense cores about the size of Earth, but with masses comparable to the Sun. White dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect that prevents further collapse. They no longer produce energy through fusion, so they simply radiate away their stored heat, gradually cooling and fading over billions of years. Eventually, they will become black dwarfs, cold, dark cinders invisible in the night sky. The Milky Way contains billions of white dwarfs, the remnants of past generations of stars. Fact 96. Neutron stars are the remnants of massive stars. When stars more massive than about 8 solar massives explode as supernova, their cores collapse into neutron stars, objects so dense that a teaspoon of neutron star material would weigh 1 billion tons. Neutron stars are only about 20 kilometers across, but they contain more mass than the Sun. They're supported by neutron degeneracy pressure, and they spin rapidly, sometimes hundreds of times per second. Some neutron stars emit beams of radio waves, appearing as pulsars, cosmic lighthouses that flash with precise regularity. Neutron stars are among the most extreme objects in the universe. Fact 97. Black holes are the final stage for the most massive stars. The most massive stars, those with initial masses greater than about 2025 solar masses, end their lives as black holes. When such a star's core collapses, nothing can stop it. The core shrinks to a point of infinite density, creating a black hole. The Milky Way contains millions of stellar mass black holes, the remnants of the most massive stars that have ever lived. Most are invisible, detectable only through their gravitational effects on nearby stars or gas. Black holes are the ultimate endpoint of stellar evolution, objects from which nothing, not even light, can escape. Fact 98. The Milky Way will eventually run out of gas. Star formation requires gas, and the Milky Way's gas supply is finite. The galaxy is currently forming stars at a rate of about 1 to 2 solar masses per year, but this rate is declining. As gas is consumed by star formation and expelled by stellar winds and supernovae, less remains for future generations. In a few billion years, especially after the merger with Andromeda, the combined galaxy will have exhausted most of its gas. Star formation will cease, and the galaxy will slowly fade as its stars age and die. The Milky Way's era of active star formation is temporary. Fact 99. The universe will continue expanding forever. The universe is expanding, and the expansion is accelerating, driven by dark energy, a mysterious force that permeates all of space. Distant galaxies are moving away from us, and over time they will recede beyond the observable universe. Eventually, in hundreds of billions of years, the Milky Way, or Milkomeda, will be isolated, surrounded by darkness, as all other galaxies disappear beyond the cosmic horizon. The universe will grow cold and empty, with galaxies becoming islands of light in an ever-expanding void. This is the ultimate fate of the cosmos. Fact 100. We are made of stardust. Every atom in your body, except for hydrogen, was created in a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were forged in stellar furnaces and scattered into space when those stars died. We are, quite literally, made of stardust. The Milky Way is not just our home, it is our origin. We are the galaxy's way of knowing itself, conscious beings made from the recycled remnants of ancient stars. In contemplating the Milky Way, we contemplate ourselves, our past and our place in the vast, beautiful cosmos. And so we end where we began, looking up at the night sky, at the pale band of light stretching across the darkness. But now we see it differently. We know what it is. We know where we are. We are inside a galaxy of hundreds of billions of stars, orbiting a supermassive black hole, surrounded by invisible dark matter, drifting toward an inevitable collision with our nearest neighbor. We are temporary, but we are part of something vast and ancient. The Milky Way will outlive us by billions of years, but in this moment we are here, conscious and aware, able to understand our place in the cosmos. That is the true wonder. Sleep well, knowing you are home among the stars.